Consider the word Mississippi. Determine all the permutations of the letters in which the 4 S's and the 2 P's must be together. Now the S's and the P's don't need to be grouped together into a group of 6, but rather the S's need to be together and the P's need to be together, and those 2 groups can be separate. To solve this question, we need to look at a large handful of cases to try and figure out what's going on. What I've drawn here on the left side of the screen is some of these cases. You'll see that I've taken the 4 S's and I've grouped them together, and I've placed those 4 S's in every single possible spot they could fit, starting with them being at the very beginning of the word, shuffling over 1 letter, over 2 letters, and so on until the 4 S's are the very last 4 letters. What you may see also is that the P's are tagging along for the ride. I have them after the group of 4 S's in every spot possible, moving along, up until this point where we can't fit 2 P's in a single letter spot, so I moved those 2 P's to the start of the word here, and that's why they remain there for the last 2 cases. Now what we're going to do is we're going to zoom in on one of these cases to figure out how many different permutations there are for this single case. And then we'll look at the remaining ones in a moment. So from our first case, and I'm talking about this one right here, number 1. Let's look at the other places where we could put the 2 P's. Okay. The thing we're not changing is that the 4 S's are at the beginning of the word, but we are going to move the group of 2 P's around. So in our first case, we put the P's immediately after the S's. Let's consider, for example, putting a letter and then the 2 P's, and then the remaining 4 letters. Or our 4 S's, 2 spaces, our 2 P's, and the remaining 3. And so on and so forth. All we're doing is moving the group of 2 P's into each of the available locations. And there you have it. We've moved the 2 P's into every single spot that they could fit in. So we have 5 cases here, and then we've got this original case. So that means that there are a total of 6 different permutations when we have our 4 S's at the very beginning. Now let's look at our second case because it is a little bit different. This second case has our 4 S's, but they are not the very start, and this changes it. So we've got a letter, our 4 S's, and then our 2 P's. Let's move those P's around to the other locations. We could have a space, our 2 P's, and then the remaining 3. We could have 2 spaces, our P's, 2 spaces. We could have 3 spaces, our P's, and 1 space. Or finally, 4 spaces and our 2 P's. There isn't another one here. In other words, I can't put a P, S's, 5 letters, and a P, because now what I've done is I've split up the P's, and they must be together. So that means for this second case that I'm looking at right here, there are 4 cases here, plus the original one, for a total of 5, not 6 like our first one. And that's only because the P's can't be split up. Now, if we were to go through the remaining cases, case 3 and 4, all the way through 5, 6, 7, we would find that each of those behaves the same as case number 2. There ends up being 5 permutations for each of those. they behave the same in that the two p's cannot be split up, and there ends up being a wasted space. The last case, case number 8, is the exact same as case number 1. There isn't a place where the p's can't be right next to each other. So there ends up being 6 permutations for this one. Whew! All right, we're almost there. What we need to consider lastly here is the group of letters that we didn't consider. It ends up being 4 I's and the letter M for a total of 5 letters. So to solve this one, we can look at the number of possibilities P, which ends up being n factorial over any duplicates. So a factorial, b factorial, etc. Well, the total number of letters in here, n, is 5. And then we divide by any duplicates. Well, the remaining letters after we've used the s's and the p's is a single m and then 4 letter i's. So we divide by 4 factorial to account for the i's and their duplicates. This means that we only end up with 5 different permutations or arrangements for those letters that I've labeled as these dashes. So if there are 5 permutations for this group of dashes, and that remains the same for every single case, 1 through 8, then if I take the number of permutations, which is 5, and I multiply that by the number of permutations in every single case summed up, so 6 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 6, which ends up being 42, we end up finally with our total number of possibilities, 5 times 42, which is 210 possibilities